In this video, I'm going to talk about the reasons for conducting non-parametric statistics. I'm also going to mention some of the misperceived thoughts about where non-parametric statistics can be applied. I think there are many people seriously mistaken about what a non-parametric statistic can and can't do. I'm also going to mention that I'm not a big fan of non-parametric statistics and suggest very briefly alternatives that I'm going to talk about in the chapter. But I do conclude that you still need to know about non-parametric statistics for several reasons. So let's get started. Non-parametric statistics were designed to test hypotheses with dependent variables not measured on a continuous scale. That is the primary reason non-parametric statistics were invented, was to deal with dependent variables that weren't measured on an interval or ratio scale. Instead, they were measured on ordinal or nominal scales. And because parametric statistics assume relatively normally distributed data, strictly speaking, you wouldn't expect them to work on data measured on an ordinal or nominal scale. In practice, non-parametric statistics convert dependent variable data into ranks. That's basically the trick of non-parametric statistics. That's where the magic is. It converts the raw data into ranked data. And that's true even if the data were ranked to begin with in your study. And there's an example in the chapter where individuals provided rankings, and you'll see that the program still converts those ranks into other ranks in order to conduct the analysis. And because the statistical techniques that are non-parametric in nature convert the data into ranks, issues of non-normality and outliers disappear. So an outlier ends up being pushed closer to the distribution, because no matter how big a value is, the largest rank is going to be equal to the sample size, right? Also, heavily skewed distributions, once the raw data are converted into ranks, the skew becomes much less substantial, and therefore the statistic can be applied on those data and be expected to yield an accurate p-value. Now, something about non-parametrics in practice is that it seems to me that people think that non-parametric statistics have no assumptions whatsoever. I've even heard people, colleagues for example, mention that the reason why they did that is because non-parametrics don't have any assumptions, and that's really quite a mistaken belief. Non-parametric statistics in fact have the same assumption as parametric statistics, except for the assumption of normally distributed scores. Non-parametrics do not assume normality, and they don't because they're going to convert it into ranks. That's the only assumption that it can overcome. So it's not a statistical analysis that can fix all your problems. So that's why I write here, non-normality is the only issue a non-parametric statistic can overcome. That's a general statement. There might be some slight exceptions here and there, but really that's the only problem that the non-parametric statistic can overcome. And I mentioned here that I'm talking about conventional non-parametric statistics, such as Mann-Whitney-U, Kruskal-Wallis, Friedman-Anova, and the Wilcoxon-Sign rank test, for example. Other statistics that might be considered non-parametric, like bootstrapping, I'm not classifying in this category. That's a different category in my mind. So even though non-parametric statistics can really only overcome the problem of non-normality, and as I mentioned in the chapter, parametric statistics like ANOVA and t-test are surprisingly robust to violations of normality and can usually cope with skew as bad as 2.0 and kurtosis as bad as 9. So what you'll learn as you go through this chapter is that I'm not really a fan of non-parametric statistics, and there are several reasons for that. Non-parametric statistics don't really test the hypotheses that researchers have in mind, in my opinion. You want to stay as close as possible to your raw data and talk about mean differences or correlations or unstandardized slopes. A 1 unit increase in this is corresponding to a 1 unit increase in that. Those are the sorts of statements you want to make in statistics, typically. Instead, when you use a non-parametric statistic, usually all your data are going to be converted to ranks, and then you start talking about mean rank differences. And it's on a scale that's really not that interesting or closely tied to what you actually measured. And you'll see examples of that in the chapter. So I prefer to stay as close as possible to the original data, because that's probably going to be the greatest opportunity for me to make inferences about my data that are most interesting. I'm also not a fan of non-parametrics because usually there are better options available. So for example, parametric statistics like the ANOVA, t-test, Pearson correlation usually work on ordinal data so long as there are 5 points or more. And that's a lot of cases in practice and research, like a Likert scale on a questionnaire, for example. You'll discover in this chapter that parametric statistics often yield accurate results on such data. I do mention, however, limited information ordinal scales, which have 4 points or less, and in those cases, parametric statistics might not be expected to work quite as well, and so you might consider non-parametrics as your option. However, there's also the possibility of conducting ANOVA, and I mention this as a generic statistic. It could be t-test or Pearson correlation, etc., on ranks, because as I present evidence in the chapter, it actually works surprisingly well conducting parametric statistics on ranked data. And finally, there's always bootstrapping. Bootstrapping also doesn't assume any level of normality, and it doesn't matter what scale of measurement you used to measure your dependent variable. I'll note that most non-parametric statistics were invented before bootstrapping was either invented or became a well-established technique to conduct analyses. My hunch is that if bootstrapping would have been invented in the 30s or 40s and was actually applicable, most non-parametric statistics wouldn't have even been invented. Despite all this, I think there are good reasons to have a fairly good knowledge of non-parametric statistics because realistically they're not going anywhere. So that's why I write you still should know about commonly used non-parametric statistics like Mann-Whitney-U, Kruskal-Wallis, Wilcoxon-signed rank test, Spearman correlation, etc. because people publish papers with those statistics, and if you're reading those papers, you'll want to have some knowledge of what they actually did. There are some rare cases where non-parametric statistics might give you a little bit more power. So it's a misconception to think that non-parametric statistics are always less powerful. There's a common saying that it's usually 5% less powerful to use a non-parametric statistic over a parametric statistic, and that's actually not true. There are cases where a non-parametric statistic will give you a more powerful option to reject the null hypothesis. At some point, I might try to provide a review of when those occasions are. The final reason you might consider it valuable to understand non-parametric statistics is that many people might not believe the arguments that I'm going to put forward in this chapter, despite the fact that I provide evidence for each argument. So people won't believe you if you say, let's just do an ANOVA on the ranks and not bother with a Kruskal-Wallis. Some people will be very surprised to hear that recommendation, and they might not believe you. So you might be stuck with doing a Kruskal-Wallis instead, even though personally I wouldn't do it. So that is a brief summary introduction to this chapter that I think is an interesting one, given how much misinformation I believe there is out there about non-parametrics, as well as little known techniques that are available to researchers that likely will provide more insightful results from your data.